Einstein's famous phrase for quantum entanglement, spooky action at a distance, has become widely known. At first glance, this phrase might be understood as a spooky effect from afar. However, the real intrigue lies in the nuance of the word spooky. In English, spooky can mean incomprehensible or supernatural or mysterious. Interestingly, the word spooky has its roots in German derived from the word Spuk, which means ghost. Keeping the meanings of the word in mind, let's briefly define this phenomenon. Quantum entanglement is a phenomenon where the quantum states of two or more particles become interconnected. This connection is so strong that, regardless of the distance between the particles, a measurement on one particle instantly, without any delay, affects the state of the other particle. This challenges the laws of classical physics and is one of the most fascinating and bizarre features of quantum mechanics. For instance, imagine two entangled particles. The moment you measure the state of one, the state of the other is instantly determined, as if there's an invisible bond between them. At this point, let's address a question that comes up in almost every video. How is quantum entanglement created? First of all, in nature, two particles can already exist in an entangled state. However, this doesn't mean that every particle is entangled. If you want to create entanglement in a laboratory setting, there are several methods to achieve this. The most commonly used method is spontaneous parametric downconversion. In this method, entanglement is achieved when a laser beam hits a special crystal. For instance, beta barium borate crystal is one of the crystals used for this purpose. When the laser strikes the crystal, a high-energy photon splits into two lower-energy photons. These photons, however, become linked to each other, producing entangled photons. This is how quantum entanglement is created in a laboratory setting. Returning to the word spooky, which we pocketed earlier, if we consider that Einstein's native language was German, we can infer that he used the word in the sense of ghostly or supernatural. And we believe no one can prove otherwise. Einstein's use of this term reveals his discomfort with quantum mechanics from the very beginning, viewing it as a kind of supernatural phenomenon. Thus, interpreting spooky action at a distance as a ghostly effect from afar wouldn't be far off the mark. A small piece of advice. Einstein, through this phrase, seemed to approach quantum entanglement not as a scientific fact, but almost as if it were a supernatural occurrence. Understanding this helps us see why quantum physics is so controversial and why Einstein struggled to fully accept this theory. To delve deeper into why Einstein couldn't embrace quantum mechanics, we need to understand the strong connection between general relativity and the principle of locality. In physics, the principle of locality states that an object is only influenced by its immediate surroundings. In other words, the effects of an event cannot exceed the speed of light and can only propagate to objects nearby. This principle is a cornerstone of classical physics and particularly of Einstein's theory of general relativity. According to the theory, mass and energy warp space-time, and this curvature propagates at the speed of light. For example, imagine a star suddenly disappearing. The effect of this event would alter the surrounding space-time curvature at the speed of light. This change would affect objects in sequence before reaching another star 1 light-year away. Consider a gravitational wave. This wave impacts the nearest particle first, and that particle influences the next closest one, creating a chain reaction. The gravitational wave doesn't jump over intermediate objects to directly affect a star 1 light-year away. In classical physics, this is how nature operates. We also observe the principle of locality in everyday life. For instance, imagine a 10-car pileup in a traffic accident. The first car in the back crashes into the car in front of it. That car then crashes into the one ahead, and so on. However, the initial car doesn't directly collide with the truck at the very front. Now, let's bring quantum entanglement into the picture. In such a scenario, the first car at the back wouldn't crash into the car directly in front of it. Instead, it would skip over the 9 cars in between and collide directly with the truck at the very front. In quantum entanglement, the moment you measure the spin value of one entangled particle, the spin value of the other particle is determined instantaneously, regardless of the distance between them. In this case, the intermediate particles are completely out of the game, and the principle of locality no longer applies. This is exactly where we think Einstein had difficulty accepting the concept. Because if locality doesn't exist, then general relativity also collapses. However, Einstein didn't outright reject entanglement. Instead, he described it as an incomplete theory. In his view, the instantaneous determination process in quantum entanglement could have a hidden explanation that aligns with the principle of locality in classical physics and doesn't exceed the speed of light, but we simply don't know it yet. The essence of his argument was similar to Adam Smith's invisible hand. There was something missing, yet to be discovered. Now, let's address a frequently asked question. How is the simultaneity or correlation strength of entanglement measured over a distance of 5 light-years? First, it's important to note that the longest distance quantum entanglement experiment conducted so far was carried out by Chinese scientists using the Messier satellite. In this experiment, entanglement was established over a distance of 1,203 kilometers between Earth and a satellite in space. This remains the strongest evidence we have so far that entanglement operates independently of distance. But if you ask, does entanglement work over light-year distances? The answer is theoretical. Quantum entanglement is explained using Schrödinger's equations and the mathematical models of quantum states. These models predict that entanglement will be preserved regardless of distance. In other words, from a modeling perspective, distance doesn't matter at all. This is where the rumors about quantum entanglement exceeding the speed of light often begin. The fact that interactions appear to happen simultaneously over a distance of 1 light-year gives the impression that the interaction speed between particles is infinite. If this interaction involved the transfer of information, we would indeed have to admit that the speed of light has been surpassed. But that's not the case. Einstein needn't worry about this. While there is a correlation between two entangled particles, it doesn't imply the transfer of information. When the result of one particle's measurement determines the state of the other, this doesn't mean that any message or data is being sent between them. The measurement outcomes are entirely random. Unless an orderly and meaningful message is transmitted, we can't speak of information transfer. This is why quantum entanglement doesn't exceed the speed of light and doesn't contradict Einstein's theory of relativity or the principle of locality. This phenomenon is not just theoretical. It's a fact proven by experiments. In 1964, John Bell developed an inequality to test the differences between quantum mechanics and classical physics. This inequality allowed us to examine Einstein's local hidden variable theory. What is this hidden variable theory, you ask? It stems from the famous paper by Einstein, Podolsky, and Rosen titled, "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" A very fancy title indeed. Bell took insights from this paper and formulated a mathematical model. To oversimplify and perhaps stretch the explanation a little, according to this model, no matter how much you measure the correlations between the spin values of two particles, the total cannot exceed 2. If this value is exceeded, the theory is wrong. What did experiments conducted in 1972, 1980, and 2010 show? This limit was exceeded, proving that quantum mechanics predictions were correct. You might wonder why it took until 2022 for these experiments to receive a Nobel Prize. We honestly have no idea. Another important result of these experiments is this: Einstein's idea of local hidden variables is invalid. In other words, quantum entanglement cannot be explained by the rules of classical physics. So, does this entanglement exceed the speed of light? No. Bell's experiments also confirmed that entanglement does not involve the transfer of information faster than the speed of light. Yes, there is a connection between two entangled particles that appears instantaneous. However, this doesn't mean any data or information is being transferred. Thus, it doesn't contradict Einstein's theory of relativity. See you in our next video.